Assalamu alaikum. Welcome to Code with Sensei. We teach programming and university topic with simple step-by-step explanation. Let's start learning.
You know that feeling, right? You write a line of code, you hit run, and poof, the magic just happens. It's so easy to take for granted, but what we don't see is that every single program lives this whole secret life, from the second you type it to the moment it actually runs. So today, we're going to pull back the curtain and see what's really going on. And really, it all comes down to this one huge question. We write code using words, symbols, stuff that makes sense to us. But a computer's brain, the processor, it doesn't speak English, it doesn't speak Python. It's like a completely alien mind. So how in the world do we bridge that gap? How does it ever figure out what we're asking it to do? Okay, this slide just nails the challenge perfectly. On the left, you've got a simple, clean command that any human can read. And on the right, that sea of ones and zeros, that's binary. And that is the only language the computer actually gets. So the whole journey we're about to take is all about translating the elegance on the left into the raw, brutal logic on the right. So before a single line of that code even thinks about getting translated, it needs a plan, right? You'd never build a house without a blueprint, and it's the exact same idea with software. You just can't write something great without a solid structure. This is, it's the foundation for literally everything else we're going to talk about.
So what do we even mean by program structure? It's actually pretty simple. It's just the organized layout of your code. Think of it like a recipe for the computer. It needs to know step by step, where do I start, what do I do next, and when am I all done? A clear structure is just a clear set of instructions, no confusion.
And here's the kicker, the really important part. A good structure isn't just for the computer's benefit. It's for us. It's for you. When code is laid out properly, it's way easier for us humans to understand it, to find bugs when things break, and to add new stuff down the road. Oh, and as a nice little bonus, a well-planned program almost always runs faster and more efficiently.
When you boil it all down, almost every single program you've ever touched does this basic three-step dance. First, there's some kind of input. You click a mouse, you type on the keyboard. Then there's processing. The program crunches some numbers or sorts some data. And finally, you get the output. Something shows up on your screen or a file gets saved. Input, process, output. That's the fundamental heartbeat of all software. Okay, so we've got our code, it's got a solid blueprint. And that structure isn't just to make things look pretty. It's what makes this next part, the translation, even possible. Now, this is where the real magic happens, turning our human-friendly plan into the machine's native language. It's time to meet the translator.
And yeah, that translator has a name. It's called the compiler. Compilation is just the process of taking all our source code and converting it, and this is key, all at once, into a language that the computer's hardware can understand directly. It's probably the most important bridge between our ideas and what the machine actually does.
But hold on, this isn't just one magic trick. It's more like a multi-stage assembly line. First, your code goes to something called a preprocessor. This thing handles some basic setup, like pulling in libraries and dealing with macros. And you can just think of macros as simple text shortcuts, basically. Then it moves on to the compiler, then an assembler, and finally a linker. Each step gets the code a little closer to its final, runnable form. Let's see how that looks.
So this flowchart here, it lays out that whole transformation for us. We start with our source code, right? Which is really just a simple text file. The preprocessor tidies it up a bit, then the compiler does the real heavy lifting, turning it into this low-level thing called assembly code. The assembler takes that and turns it into pure machine code, what's called an object file. And finally, the linker grabs that file, pulls in any other bits and pieces it needs from libraries, and stitches it all together into one single program you can actually run. It's an amazing journey from a text file to a real application.
But here's the thing, the compiler isn't just a translator, it's also a super strict gatekeeper. A huge part of its job is to act like a proofreader, checking our code for mistakes. Did you forget a semicolon? Did you misspell a variable name? The compiler just stops everything right there and says, nope, go fix this. It's a really critical quality check that makes sure broken code never even gets close to running. All right, so our program is written, it's well structured, and it's been compiled. It is now a lean, mean, machine-readable file. So, what happens in that tiny split second after you double-click the icon? What happens when you press Run? Well, now the computer finally gets to take center stage.
We call this the execution flow, and it's exactly what it sounds like. The precise, step-by-step order that the computer's processor, the CPU, is going to follow. We're not talking about big ideas anymore. We are way down at the microscopic level, carrying out one tiny instruction after another, but at a speed that is just almost impossible to imagine.
And that CPU just runs on this relentless, crazy fast cycle. First, it fetches an instruction from memory, grabs the next thing to do. Then it decodes it, figuring out what that instruction actually means. And finally, it executes it. It performs the task. Fetch, decode, execute, over and over, billions of times, every single second. It's mind-boggling.
Okay, let's make this super concrete. Imagine our program has this one simple line of code in it. To us, it's one simple action. But to the CPU, oh, it's a whole sequence of tiny little steps.
So to execute just this one line, the CPU has to do a bunch of little microtasks. Let's pretend x is 5 and y is 10. First, the CPU has to go fetch the value of x from memory. Then, it has to go fetch the value of y. After that, it sends both of those numbers to its little math brain, that ALU we talked about, to actually do the addition. And finally, it takes the answer and stores it in the memory spot we called Z. So what looks like one single instruction to us is actually this whole carefully choreographed dance for the machine.
So there you have it. We've gone all the way from a human idea down to what the machine is actually doing. But why does any of this matter? Why go through all this? Well, because understanding this whole journey connects the what we want to do, with the how the computer actually does it. And knowing that helps us write code that's smarter, faster, and just plain better.
You know, understanding compilation makes even more sense when you look at the alternative, which is called interpretation. This table breaks it down nicely. A compiler, like we've seen, translates the whole program at once, before you ever run it. That usually makes the final program really fast. But an interpreter, which languages like Python use, translates your code line by line while it's running. It's a bit more flexible, but generally a bit slower. And then, just to make things interesting, you have languages like Java that use a really clever hybrid approach to try and get the best of both worlds.
Okay, let's nail down the big takeaways from all this. Number 1, structure is everything. It's the blueprint. Number 2, compilation is that crucial translation step that gets our code ready for the machine. 3, the CPU lives by a simple, super fast cycle: fetch, decode, execute. And really, it all comes back to this one idea. Having a good structure isn't just nice to have. It is the secret sauce for making software that's efficient and doesn't break.
And you know, there's this quote from the material that I think just sums this whole thing up perfectly. It says, "Code is written by humans, compiled by systems, and executed by machines." And what connects all three of those worlds? Structure. That's the golden thread that ties the human idea to the system's translation to the machine's final action.
So, the next time you hit that run button, hopefully you'll have a little picture in your head of the secret life your program is living. You'll see the blueprint, the translation process, and that final performance happening on the silicon stage. So, now that you know about this incredible journey, from your mind all the way to the machine, what are you going to create with that knowledge?
So that's a wrap. If you enjoyed this video, please like, share and subscribe. Zarur karen. Don't forget to leave a comment below and watch the next video in the playlist. Khuda Hafiz.